All right. So in this case, I need us to consider a recap on our power supplies as we had this in our info. So if you're to consider this activity that you're going to have, it's actually going to be a recap of what we had in our info. So number one, we are given that a mains supply of 240 volts AC is fed into a transformer with turns ratio of 8:1. So remember, from your transformer, we understand that 8:1 is the transformer ratio that you'll be given. And this transformer ratio that we have from the number of turns, considering the primary to the secondary, we can consider this the primary to the secondary, which is equal to the voltage of the primary to the secondary, which is also, when it is to the current, is going to be the secondary over the primary. Remember that these values that you'll be dealing with are referred to considering the voltage and the current. These are referred to as the RMS values. So whatever that you're going to be having, the VP on the primary is going to be the RMS, the VS at the output, there will be RMS values. So they were given that it is fed with this, which is the supply in the mains. So this is the mains, meaning to say we are talking of what? The primary voltage. So there we are given the primary voltage, but like I said, these are RMS values, remember, from our info. So this voltage that we are given is the RMS voltage. So we are given, in this case, that is VP of the primary side, which is given as 240 volts. But like I said, representing what? An RMS value. So it is fed into a transformer with a turns of 8:1. So this is the ratio. As I said, it can represent anything. Is it the number of turns, the voltage, the current? So that part there is the one that is representing 8:1, which is 8/1. So you can relate depending with what you're asked to calculate. It can be number of turns, it can be voltage, it can be current. You equate to 8/1. Then we're given that the secondary output supplies two unfiltered rectifier circuits. So take note, the output, whatever that you're going to have is going to supply. So you're going to see, and they are unfiltered. We're going to talk about the filter circuits in our next classes. So this is unfiltered. So we're going to talk about this part of the supply to the rectifier circuits, which is going to affect a half wave and a full wave. All right, so let's answer this first part, which has nothing to do with what is happening on the rectifier. Calculate ignoring all voltage drops the transformer output RMS voltage. Remember, as long as you're dealing with the transformer, these values that you're having, unless you are given or stated otherwise, these values are RMS values, the voltage and current. So meaning to say, in this case, they are simply asking you to calculate VS, the output voltage, which is the RMS voltage, all right? So meaning to say, we can use our ratio. Remember, our transformer ratio that we have, remember, it can be used. This voltage can be equated to this. Is it current? Is it the number of turns? Anything that you're given. So in this case, we need voltage. So we're going to take the part of the voltage. VP over VS is equal to 8/1. So from this, we are given the input, which is the RMS voltage of 240. So you're just going to substitute. That is 240 over VS is equal to 8/1. So as you can see, we formed an equation where we can solve for VS, just cross multiply. That's 8 VS, product of this. Then 240 times 1, which is 240, simply divide by 8 both sides. That was going to give you the voltage at the secondary side, which is the output. And this value is an RMS value. So that is 30 volts. So you're talking of what? The RMS value in that case, this one. Input also on the primary side is the RMS value again. Okay, the primary current, if the secondary RMS current is, we are given the secondary current, we need the primary current on B. All right, so in this case, like I said, this ratio can be used even for currents. So we can relate the currents, but take note for current, it's IS over IP, secondary over primary. So meaning to say IS over IP is equal to the same ratio that you're given there of 8 over 1. And these are RMS values that you're talking about. So meaning to say, given a secondary, in this case, a secondary RMS current of 1,6. We have it. So meaning to say already we've got the value of IS, which is 1,6 amps. What is going to be the value of IP? Which is an RMS value again. So it's just a matter of substituting. IS we have, which is 1,6. So that is 1,6 over the primary current, which is equal to 8 over 1. Cross multiply to find the value of IP. That was going to be IP times 8, which is 8 IP is equal to 1,6. If you cross multiply these two, so you can simplify this current by dividing by 8 both sides. That is giving us the value of the primary current, which is an RMS value. So that was going to give us the value of the primary current, which is 0,2. So that is what we have in this case, primary value. And also here, the secondary value, which is, and these are RMS values. All right. So this is just a recap. As you can see, guys, nothing has changed from our info. Now with the information that you're given, that the output, take note, they're saying this output that we have here, which is our RMS voltage. What is it about the output? The secondary output supplies two unfiltered rectifier circuits, meaning to say you're talking of the part where the filter is not considered. It is going to supply two rectifier circuits. The output that we are seeing, it will enter a rectifier. One, it's a half wave. Another one, it is a full wave bridge rectifier. So now they are saying calculate for each of the rectifier circuit, for each, take note, number 2, calculate for each rectifier circuit. So we're going to consider the full wave and the half wave. All right, so in this case, I'm just going to put this one side. This is our VP. Remember, we're given this VP and we calculated VS, which is the secondary side. We need this VS. Remember, it is the secondary side, which is being what? Connected to the rectifier circuit. So we are going to consider that. And this is an RMS value, okay, which is the RMS voltage at the output of the transformer, but it will be fed into the rectifier, and out of these rectifiers, we've got two to be considered, a half wave and a full wave. So we are going to consider two calculations here for a half wave rectifier and also for a full wave rectifier. All right, considering this, like I said, here we are not going to have anything new in terms of our calculations. Let's check the first part that we are given. This was to calculate, number 1, the peak rectifier output voltage. Let's consider for a half wave. What is it that we have? Remember from our N4, if you still remember these formulas that we had on our half wave rectifiers calculations. If you are to relate the maximum voltage, which is VM, it can be calculated from what? From the maximum, from the RMS voltage, we can calculate the maximum voltage. So VM is 1,44 times what? The RMS value, of which we have that. We have the RMS value. The RMS value is which one? The secondary. Remember this VS, it represents what? The RMS. Remember, it is the RMS voltage that you're calculating there. So meaning to say, we can calculate the peak rectifier output. So the peak, that is VP, you can write it as VP like this. You can write it as VM like that. Maximum, that is the peak. So you saw that from the formula. That's 1,414 times the RMS value, which is VRMS, with the secondary side that we got on the secondary. The secondary is the one that is connected to the rectifier. So we're going to use the 30 volts, our VS. So that was it. So multiplying this, you're going to obtain 42.42 volts as our maximum voltage. And this does not affect even for a full wave. The maximum voltage is still from the same formula, even for a full wave. So this was not going to affect anything. We're still going to use one and the same RMS value at the output, which is 30. So we're still going to obtain the same answer in that case. That is our maximum value. It does not affect. On B, you need to calculate the ripple peak-to-peak voltage. All right. So without any filtering that can happen in this, because remember we are told here, we are told that it supplies to unfiltered, meaning to say we do not have any filtering. We do not have that. So in this case, the formula is going to be adjusted to the maximum, in that case, value. So meaning to say the ripple peak-to-peak voltage will be equal to the maximum voltage when you are considering a circuit like what we are given there that has no filtering, because we are given that it has no filtering. No filtering and smoothing is considered there. It is not considered. So your ripple voltage, ripple voltage peak to peak is going to be the maximum, which is the one that you calculated already here. So meaning to say our answer was still going to remain as 42.42 volts. We already calculated this, which is also the same on this other side of a full wave rectifier. We were still going to obtain the same value as VM, which is 42.42 volts. There's no effect there. So this time you have to consider that filtering is not there. So what is going to happen? It's just going to be the maximum. All right, let's consider another part, which is, in this case, you're now asked to calculate the ripple RMS voltage. Okay, so also we had this from our calculations, if you still remember from your N4, the ripple RMS, which is the ripple voltage. You had these calculations, which is not going to change. 0.385 times the maximum value. So we have this for considering if it is a half wave. Okay, we are on the half wave. We have to consider we are on a half wave. This part here is for a half wave. This part, we are still considering on a half wave calculation. This is going to be 0.385 times what? The maximum value. So this case, we need our ripple voltage. Our ripple RMS voltage is equal to 0.385 times the maximum value for a half wave. What about for a full wave? For a full wave, this ripple RMS voltage is given by 0.305 times the maximum voltage. We are given this is a full wave bridge. Remember, we're given that it's a full wave bridge. A full wave bridge in that case. Because you can consider to be a full wave, which is a center tape or a bridge. So for a full wave bridge, so you're not supposed to forget that. So this is what you're going to have. So as you can see, it's just a matter of knowing which formula to use under which rectifier. So it will be very, very important that you do relate your N4, because they will be thinking that you already know that because you already covered that. So you won't be given all of these formulas. They will be thinking that you already have it from your N4. So they're just going to multiply 0.385 times the maximum value as we had it under this side. Remember, our maximum value was 42.2. So that was going to be, that was going to give us 16.332 volts. which is our RMS ripple voltage. Considering for a full wave bridge, we are going to multiply by 0.305 times the maximum voltage, which is, we had the same maximum voltage this side, 42.42. So this was going to give us 12.938 volts. So that is what we have there. So as you can see, guys, it's just a repetition that we are still having. So consider, what are you working with? On D, we are asked it now to calculate the DC average voltage. The DC average voltage, considering your VDC. So how would you calculate it considering a half wave? So also we have got this, okay? So we need to calculate VDC, which is our average voltage. Okay, so that's D. So the average voltage is given by VDC. Considering a half wave, our VDC is taken from maximum over pi, which is given as 0.318 times what? Times the maximum voltage, 0.318. From N4, we have this. Or just use Vmax over pi. So as we saw from this, Vmax over pi, it simply gives us 0.318 times the maximum voltage, which is, that's our VDC. So we have got this 0.318 times the maximum value. Remember, your VM here is still the same, 42.42 volts. So this was going to give you the average DC voltage. That's VDC was going to be 13.490 volts to 3 decimal places. Considering, on the other hand, of a full wave, working with a full wave bridge, because this is now the side. You're considering a full wave, which is a bridge. You're going to have your VDC, in this case, is given. This time it will be 2 Vmax over pi, which is the value that will be equivalent to 0.637 of the maximum value, which is our VM. So meaning to say that is going to be affected by 2 on top, 2 over pi. You're considering a full wave bridge. So that's 0.637 times our Vmax. What is our maximum voltage? As we had before, it was 42.42. So we're just gonna use this as it is. So that was going to give us an average DC voltage of 27.022 volts, as we are to consider our average DC of a full wave. So we must consider both full wave and half wave. Then on E, they need you to calculate the ripple factor. So the ripple factor also, guys, these formulas you're given from your formula sheet, so you're not supposed to worry much. You just need to know which one exactly they want to use, because they won't write for you to say this is for a half wave, this is for a full wave bridge rectifier. You're supposed to know which one is for a half wave. All right, so considering the ripple factor, remember that the ripple factor R is simply from the ripple voltage, which is our ripple RMS voltage, over the average DC voltage. And that is the same even if we are to consider for a full wave. That is our ripple RMS voltage over what? Over the average DC. So that one is just to use accordingly, meaning to say, according to the half wave, our RMS ripple voltage, the one that we got, remember, RMS ripple voltage, it was 16.32, this one, 16.332. So you're just going to take that. Your VDC was 13. So you have these values. So that's 16.332 divided to the VDC. You already have this value, which is 13.490. Okay, so that was going to give us the value of R, which is 1.211. With the same calculations, we are going to obtain the ripple factor of a full wave using the ripple RMS value that we got on a full wave, which is this one that we calculated this side, remember? That is our ripple RMS. We got 12,938. So we're going to take this one, 12,938 divide to our VDC, which is 27.022. So this was going to give us the value of R, which is going to be 0,479, just like that. So you have to consider what are you given? Like, are you working with a half wave? Are you working with a full? So all that part from our N4, as it is supposed to be applied. It is supposed to be used. You're supposed to apply the concept, revise as much as you can all the basics that you had from the transformer ratios to the rectifier circuits to the filter circuits. This one, it was unfiltered. So we're going to see other questions when you're going to be working with those filter circuits. So that's it, guys. Till we meet again.